Okay, so a very good afternoon to everyone. Welcome to IDS 576. I hope I'm audible to everyone. If if it is, one of you can just type it in the chat or just use your mic.
Yeah, audible.
Okay, that's great. So I think in stuff, I know many of you have other courses and you've gone through course logistics and so on several times this week. So let's also go through course logistics today, and then we'll get started on the first lecture. Okay, so um, my name is Teja, for folks who have not taken a class with me before, and I'm also faculty in the IDS department. This semester I'm going to be teaching 576, which is deep learning and modern applications. So if you're not in 576 but happen to have the Zoom link, there's a good time to check your registration and stuff. Or maybe you need to go to another course. So let me share my screen and just walk you through some material that is already linked on Blackboard, but I wanted to spend some time on that. So let's see. Okay, so first thing, everybody should have access to Blackboard. If not, if you have registered late, like for example today, it will get auto-populated soon. So Blackboard is not a hard dependency at the moment, as we will discuss right now. But eventually, you do want to have access so that you can submit assignments and stuff. Okay, so this is how your page should look like. So basically, there are 5 key links on this course page. The first link is actually just a page which links to an external website. In this case, a GitHub repository. Okay, so that repository is where you will see most of the at least syllabus and learning goals and things like that will be present. Okay, and also some example Python notebooks that will be useful in our course. So the second link out of the 5 is announcements. Announcements, as you all know, is just a link that kind of archives announcements that the teaching staff, me and the TA, may send you. So you may get an email immediately when we send an announcement or at the end of the day, but it'll also be archived here, so you can go back and check what the announcements were. The third link is uploads, and so this is related to the assignments and project components of this course, and I'll discuss that when we walk over the course structure. But if when you finish the assignments or projects, there is a deadline within which you want to upload it at this link. Okay, and the fourth link is Zoom. So everybody is here, hopefully on Zoom. So if some of your friends don't have access to Blackboard and they are in this course, if they reach out to you, please give them the Zoom link. I've also given the Zoom link to a couple of students who have emailed me, but hopefully it'll iron out soon. And the last link is a discussion board. Its utility is, depends on how much you want to interact with other students through this formal channel. Of course, you can also interact through other channels. So that's the discussion board component. Okay. So I just wanted to walk through this Blackboard structure just to say that, hey, there's nothing missing here. These are the key components. And much of the stuff is actually in a GitHub repository, okay, in a Git repository, actually. So with that, I hope everybody has access to this repo. So what I'm going to do is just walk you through the components of the course. And one good thing you can do is clone this repository. So maybe towards the end we can talk about it. And it has the examples as well as some. It also actually has slides. And assignment components. So if you want to clone it, and then you can always git pull and get updated in case there are changes. Okay. So let me talk about the course structure. So this is a 4-credit course, so it is fairly intensive. So this is a course which kind of, you can think of it as a complement to 572 or 575. Some of you might have done it. So it's focused on a subtopic within the broader area of machine learning and data mining. Okay, so the subtopic is about using neural network architectures for working with large data sets which are atypical, non-tabular data sets, for example, images, videos, audio, other types of data sets. So unstructured data sets, for example, text. Okay, so that's kind of the scope of this course. So we'll look at several popular deep learning architectures, and it's an evolving field over the past decade or a decade and a half. It has really grown exponentially, and so there are many models and variants. Instead of looking at all of them, which is hard to do, we're going to look at a few very popular models that have surfaced over the years. Okay, so a very short list is here. So convolutional neural networks, recurrent neural networks, attention mechanism and transformer architecture, variational autoencoders, generative adversarial networks, and then we'll also actually, this course is a little bit different from a typical deep learning course. We'll also focus on decision making. And so in particular, a variant of decision-making paradigm is called deep learning. It's called reinforcement learning. And we'll merge reinforcement learning, which is a concept in itself, with deep learning. And so it's called deep reinforcement learning. And we'll see that as an example of how to tie predictions to decisions. Okay, so the usual machine learning to decision making. So so those are the components. And as we run through the course, we will kind of spend enough time on each one of them. So right now, although I'm throwing some words, those are just for, in case you've heard these words before, they're just so get a sense of like what are some keywords related to this course. And in fact, in the lecture one, we're going to again revisit some of these. Okay. So there's several previous links from previous versions of this course. So it has been offered several times. But what changes over time is actually some material, is no more new or no more popular. For example, there used to be a component of graphical models. We are not covering it now. We have introduced transformer architectures, for example. So there are some changes that happen from semester to semester. Okay. Meeting times, Thursdays at 3:30. It's mostly a lecture format, with maybe occasionally jumping into looking at a Python script or equivalent. It will be on Zoom, and so you will have hopefully a recording that will be auto-populated in the same Blackboard link, so you can see a recording in case you want to recheck the lecture or you happen to miss it. Okay. Office hours are on Thursdays before the lecture, and we have a TA, Saket, who is a PhD student in the department, and his office hours are on Tuesdays from 3 to 4:30 on Zoom. I think I have a Zoom link. I believe I didn't push the update, so you are not seeing it here, but you can find a link here as well as potentially on Blackboard. So it will be updated by after this lecture. Okay. So let's look at the timeline. Okay, because even before getting into concepts and so on, so let's look at as well as the grading and all that. Let's look at timeline. So there's approximately 12 or 13 lecture days, okay, out of the 16-week course. So what's happening on the remaining days? So let's look at it. So in this states, and this is very useful for you as well to plan your bandwidth in terms of finishing up assignments right before they're due. So assignment 1, for example, due date is Feb 2nd, so it's about 3 weeks from now. So I have added an extra, I guess, tag to each of the lecture. Like for the first 2 weeks, it's going to be online. There may be a couple of lectures that will be, or one lecture that's currently online due to me traveling. But if it doesn't pan out, I'm going to drop that. So the other lectures, other than the lecture days themselves, are actually assigned for another purpose, which is to actually get you to be, get you to make progress and report that progress and discuss that progress with the teaching staff. So in particular, a couple of lecture slots will be repurposed for discussion and updating and brainstorming, if there's hiccups or hurdles that need to be crossed while working on the projects. Okay, and so we'll talk about the projects in a second, but a teaser is that projects are a big component of this course. And in fact, you'll see if you get feedback from previous students who have done this courses previously, it is where you can actually try out something, really understand and really hit some limits. For example, computational limits, maybe conceptual limits, or maybe you're able to do something very interesting with your, a particular domain, a data set from a particular domain, or application from a particular domain. So this really is something which is the focus of this course. And you can see that there is actually, for example, no slot for a midterm, and there's actually not going to be an end term as well. So and the last slot is reserved for presentation. So there'll be teams of you who will be working through the assignments and project, and I'm going to mention that in a second. But the last slot is to present your projects, okay, to other students. So let's actually look at those components. But before that, textbooks. There are actually several textbooks available, which are actually some of them are free. Freely accessible, or if not completely freely accessible, a draft versions of them are freely accessible. So these are some textbooks listed here. Depending on your style, if you really want to get into a lot of depth, then Deep Learning is a really good book by that name. It's a little bit dated in the sense that it's 5-6 years old. So dive into deep learning by some really good researchers from I think Amazon. Is a book which comes with its own a nice, I guess, complements topics with code. So it's also I guess openly available, so you can certainly look at it. Deep learning for coders, as the name suggests, it's for folks who are kind of don't want to spend too much time in the math or some more formal machine learning treatment of the topics, and try to get code and then try out a more intuition driven approach. Then that's a good book to look at. Okay, and all these are just for depth. Okay, we are going to cover our slides will be sufficient for much of the course, but if you want to get into depth and if you have prefer a certain style, then these are some good references to go. And for the decision making part, I would say Reinforcement Learning: An Introduction is a really good introductory book for an in-depth understanding of reinforcement learning. Okay, of course, we're going to cover that in these lectures. There are other sources for understanding reinforcement learning, other full-fledged courses, as well as tutorials. But these are some good starting points. Okay. Software, we are going to be using Python throughout this course. Folks who have no exposure to Python, that's a alarm bell. You should certainly have some experience with Python, beginner level, ideally. And by beginner level, I don't mean you should have written some decent programs. Okay, so some decent scripts. So for example, we'll be using, so some of these packages should be familiar to some of you. SciPy, NumPy, Pandas, or maybe you have used scikit-learn. There'll be some packages that will be new for some of you. So that will cover in the course. Okay. So plotting. So if you've used R and if you're pretty mature with R, then Python, and you've never done something in Python, it's still acceptable. But you should have some programming experience, because all the assignments are require you to spend time in code and try to debug or understand your modeling, training, its performance, and so on. Mostly, so okay, let's talk about computation, because that's a very important thing for especially deep learning based exercises that which are in our assignments. So we will rely on the generosity of Google to use Google Colab most of the time. So you can click on that link, and as long as you have a Google account, for example, UIC uses Google Workspace, so you should be able to get free GPUs, which are general, graphics processing units to train deep learning models. Okay, so we'll discuss that. As you get to assignment 1 and 2, you will want to use a GPU. If you have access to a local GPU, that's great. But we can discuss that more about this. So actually, there's some question. I'd never set the rules for questions, so you can certainly ask questions in the chat, or raise a hand, or directly unmute yourself and talk. So please go ahead.
Yeah, so I see that you've mentioned that we should be using Linux if we have any issue, any if you're in doubt. So my question
Okay.
is, will the GPU mechanisms that we're using algorithms, will
Yeah.
they work on Windows without issues, or will we have
So
to look at?
mostly, okay, so I guess this is a little bit dated advice. So even on Windows with Windows subsystem for Linux, you actually get not a virtual machine, but I think it's a container, or maybe it's a virtual machine. I don't know. So WSL actually encompasses this aspect. So um, if you have a laptop with a GPU that is actually capable of training, which is like, for example, an NVIDIA GPU, okay, some low end or mobile GPU, and you want to use it, you don't need Linux. Okay, you can actually use Windows directly and work with that GPU. Okay.
Okay.
So this is just, so I think, for example, I think the most standard format for folks who use Windows and let's say Mac is to just use, for example, Anaconda Python distribution. So you just you install it, and you get with a few clicks, you can get to a Jupyter Lab instance, right? And once you are in the Jupyter Lab instance, this is the usual Python scripting. So that's what you can do on local machines, which is what Google Colab also provides. The additional aspect being with Colab, you can actually collaborate with people. And that's, I guess that's a good point, as well as, of course, a good point is sometimes you can actually, not sometimes, but most of the times you can get a free GPU. But mostly, most of the work will be in basically Jupyter Lab or IPython scripts.
Okay.
Yeah, so there's a question by Robert. If I decide to use a local GPU, do you recommend NVIDIA or AMD? So good question. We are actually just going to be using NVIDIA GPUs here. AMD support in software, it is building up. As I said, the field is expanding and exponentially growing. All sorts of new solutions, and AMD is also providing decent solutions as of today in 2022. But we have been using NVIDIA and NVIDIA-based software at this point. So that's what we are doing right now. Yeah. Recommended distro. I mean, there's actually no recommendation for distro. This was just saying that any OS is okay. So the most important part is, if you want to train large-scale deep learning models, or not large-scale, let's say moderately heavy deep learning models on your laptop, it's not possible. Okay, in the sense that it is possible. For example, assignment 2, I'm just jumping over 2 steps now, but assignment 2 has some as a problem where you need to train a image classifier. Okay, training that using just CPUs, by the way. If you want to just use a laptop and your laptop doesn't have a GPU, training on CPU just takes a long time. It's just too long, and it's even to do like a couple of iterations of whatever computation training steps that you want to do. So whereas if you do that same thing with a GPU, either local or on the cloud, it's faster, and it's faster not by 10%, 20%, like there's a multiplication factor there. Okay. But any OS is okay. Typically, like for example, I'm using Linux, but today in today's world, I think it really is just your convenience. You don't have to switch OS just for this course. Yeah. What should we expect in lab sessions? So lab sessions are actually, I should say and are, because it's actually, so historically, like there's been a different levels of different sizes of the audience as well. Sometimes the course has 15 students, sometimes the course has 30 students. And so currently office hours will be used depending on, if it's a lot of students, then it will be like a broadcast situation, or if there's only 1:1 interaction between the TA and students, then it's just office hours. Initially, the TA is gonna, the hope is that TA will help you iron out software or setting up issues. You will see that for first assignment. So the assignments are set up such a way that you'll not have huge computational issues or huge software issues in the first assignment. But for second assignment, you want to be ready with, hey, now I know how to work around Python, how to submit an assignment, how to do some minor things with Python scripting. Now, second assignment is where you will kind of want to use a GPU, and you'll see the use of some other software like PyTorch and so on. So it slowly ramps up. So accordingly, we'll ad hoc figure out if a lab session is needed. Okay, so as a formal sense, right now we have not planned anything. It just depends on the feedback from students and if everybody is facing a difficulty, or if one team, or if one needs a little bit of help. I think I digressed there a little bit. Let me come back to textbook software. Okay, I just wanted to wrap this up, which is about assignments and project. As I said, this course is really an elective course. You chose this because you want to at least have a formal journey with deep learning. You can always do learn things from really top-notch folks at other locations, right? It's not just UIC or IDS, which is able to teach you deep learning. So the focus of this course is really to have that bandwidth dedicated to learn deep learning in a nice uh, you know evenly paced way over the next 4 months, 3 months, and do the assignments which expose you to different basic models or the most popular variants of deep learning architectures, and then hopefully prepare you to a professional career as somebody who works with deep learning models, or prepare you to further dive down into a specific area like natural language processing or vision or audio, or even tabular data but use deep learning. So there are many avenues that you could pursue in depth, but this course is just to have a nice journey through popular deep learning architectures that have become popular in the past decade. Okay, so in that sense, since you're interested in selective course, it's really focused on the project. It's really hands-on. All the assignments and the project, of course. There are 4 assignments, so actually quite evenly paced every 2 weeks or 3 weeks. So they have to be done in groups of 4, less than or equal to 4. So if you want to be super challenging, if you want to have a lot of challenge in this course, you can always choose to do with groups of 2 if you want. And there is a spreadsheet linked here. It's only accessible to UIC IDs. So there you can try to find teammates through that channel. Like you can put your name so that, as well as email, so that you can contact between each other. And eventually, once you form a group, you can also put your names as team members in that same spreadsheet. It's a single sheet spreadsheet. So this will help us. This will help us for our UIC system as well. So where we will, the Blackboard system as well, where we'll have to group you guys when you submit the assignments and projects. The assignments are already up in the repository if you want to have a quick look at them. But they have strict deadlines, and the expectation is that you do plan your calendar beforehand. Okay, so you have an explicit list of dates, and when assignments are due, go to your calendar, put these things in, because if you don't allocate time and at the last moment you want one extra day because, hey, I didn't realize training 100 steps of doing some training for a neural network is taking too long, that's something you need to plan in advance. Okay, so advanced planning is going to help. Late submissions have an automatic penalty of 20%, which is not too much, 20% of assignment component, but it's something to be cognizant about. So the same group. Okay, so both for project and assignment, it's the same group, and the project component is basically open-ended, and that's why there are several contact points. If you saw in the schedule, to talk to teaching staff, me, and the TA, so that you really spend time and do are able to successfully complete your project. And so it's open-ended. You can come up with ideas based on your own domain expertise from before, from your working life, or whichever field you want to get into, or from your previous courses. You can conceptualize a project. There's a lot of details listed in the project link here. Okay, it's another notebook in the same repository. So it gives you a sense of what's the scope, what's the evaluation criteria, what are some examples, and it gives you links to some example data sets and some example web pages that you can go to get a sense of what could be an interesting project. Okay, historically, like in the last semester, folks have worked on music generation, several very, very different projects, music generation, recommendation, the ones I remember, of course, image captioning and few others. Okay, so actually reinforcement learning, trying to make an agent walk in an artificial setting and so on. So there's, that's just an example, but there are several other examples in the note, in that link. So, and you'll of course be talking to us, so we will be able to figure out whether the project meets the requirements of this course. Is it at the right level? For example, it should not be too ambitious that you need a lot of compute to do it. So again, same idea. And the idea is that, it's a project is an important focus of this course relative to maybe other courses which also have a lot of other things under project component. So through the project is where you will kind of flex your learnings and really understand like what it takes to go from conceptualization to actually building a successful deep learning model in your domain of interest. So as you can see, since I've been emphasizing project quite a bit, you can see that project is really a big part of the grading. So it's actually 60%. So, and it's split between an intermediate check-in, where you'll have a 2 or 3 page check-in of what you've done so far, and a final check-in, which is 50% of the grade. The assignments are 8% each for the grade. And there's also a 8% for course participation, which is actually just being a good course citizen. You want to be attending, if not all, most of the classes, interacting with the instructor and RTA, ideally both, and also how well you support your group. Okay, and I know many people from some of my other courses I've taught are sometimes they're hesitant to form groups. For example, if there's a large group, but it's really important that you work together and do a good job with both assignments and project. Okay, so you want to support your group and not do anything and just be a slack in the group. Okay, so it's important. Um, any questions about the logistics? So if you have questions, they may come up, maybe 5 minutes later, or maybe even after the lecture. You can always send me an email or ask to chat, like I just see one here, or you can also unmute yourself and ask directly. Okay. So the question is how many participants? It's actually less than equal to 4. It's strictly less than equal to 4. For definitely 5 is not going to be allowed for sure. If you want to do 4, that's fine, but less is also fine. Okay. Sometimes some students want to have a little bit more challenging, I guess, experience. They have a little bit more bandwidth, depends on the course, other courses they're taking, and so on. Okay. So with that emphasis that you need to have definitely, if you have zero Python experience or very little programming experience, this course is not going to help you learn Python and do this at the same time. So folks who have done recently 575 or 572, you probably are pretty well prepared. But folks who are, are still, like if you're on the coding side, this elective may not be the best for you if you and we're not looking for software engineers here or any expert programmers, but you want to be comfortable using, for example, NumPy, in dimensional arrays, or using matplotlib, or basic Python data structures. Abstract data types like dictionaries, lists, and so on. Okay, so let me now discuss the lecture for today. Okay, so I'll not go through this whole list, but you can see there's a bunch of at least titles of what each lecture is going to be about. We will discuss them as we navigate, and in fact today we will see a more high-level picture of the overall journey in this course. But for today, the objective is to, once I go through this overall outlook of this course using slides, and the slides are linked here. The slides are in this repository. Sorry, maybe they're linked somewhere as well. Let's get you. Oh, there's no explicit link to the slides, is it? Okay, so actually, the slides are in the same, repository. So you can just go to slides, and you can't open it here because PDF rendering, or maybe you can. I haven't tried it. Oh, you can. Okay, but you should just download it. You can download the whole repository using just, you can download it. If you just want a snapshot without version control, you can just do download zip. Or if you want to clone it, because there's also examples and maybe they'll get updated, so you can also git pull the repository. If you don't know what git pull means, don't worry. For now, you can just download and work with that. Okay. Yeah, actually, I was going to say something. Did I do 2 steps forward? Okay. Oh yeah, slides are there. Link is here. Yeah. So today's goal is to get a sense of the overall content of this course, at least a little bit more exposure than the course logistics that I've gone through. And then we will do 2 things. One is recap a typical machine learning pipeline. Okay, and in particular, we'll just look at a classification problem. Again, it's just a review. We'll look at the 4 key components that kind of define a classification problem. And so we'll talk about a little bit about data, a little bit about models, a little bit about the loss function for selection criteria, to select a good model, and also how to even do that selection, which is through optimization. Okay, so which is to compute. So those are the 4 components that we'll briefly review. So it should be a review for folks who've done 572 and 575 in the department. But even if you have not done those 2 courses, that's fine. It's just a review of a typical machine learning workflow. So you have a good sense of like what are the moving components. And the second concept that we'll introduce today is backpropagation. It's a new word, but behind the scenes, it's just calculus. And so we will work through a couple of examples and get acquainted with backpropagation. So there's also a link to lecture goals. So let's look at the goals. There are 4 goals. First is to understand the key components of classification task. Second is, actually there's not in the right order, but second is relate business problems to machine learning methods. It's just a brief commentary on how important is machine learning. I mean, in some places it's super important, some places it may not be. Third thing is how chain rule works. So chain rule, backpropagation, I guess is part of calculus. So we'll look at that. And then the last one is understand why multi-class logistic regression may not work well even for 2-dimensional data set. Okay, so we have a small example towards the end to motivate why you need nonlinear models anyway. And in nonlinear models, maybe we can use deep learning models. Okay, so we'll talk about linear models, nonlinear models in a second, later. So these are the learning goals. Here's a quick, sorry, this is a link that I want to just show you where you can actually do a full machine learning workflow in the browser. So you can do it in the browser. So try this link out. It will give you a little bit more motivation or a little bit more interest. It'll generate a little bit more interest in what we're talking about. Okay, so with that, let me actually switch over to my slides. Okay, so we are really getting started in terms of the content of the course now. But I'll still again go through a little bit about an intro to the course, which is really about the content. Hey, what are we going to kind of touch in this course? And then, as I said, we'll do a brief review of classification and then look at backpropagation as a concept. And last one is just, although it says feedforward neural networks here, we're going to be just talking about why logistic regression can fail even for a two-dimensional data set. And it's a very, it's a synthetic example, but you'll get a feel for, already a little bit of power for why you would want something interesting like a deep learning model or a neural network model. Okay, so the topics, as I mentioned briefly before, we'll cover several different models. Okay, so it's very similar to how you look at a bunch of supervised learning models, right? You might have looked at a bunch of supervised learning models before. Look at a bunch of models under the umbrella of two ideas. One is deep learning, which basically encompasses neural network-based models. And the second one is what is called reinforcement learning. So it's really related to making decisions. Okay, so those are the two buckets of topics that we look at. And so, sorry. But before I talk about the specific, these two buckets, deep learning and online reinforcement learning, I want to give you a big, I guess, disclaimer. That's what this slide is about, which is that if you really zoom out, we are really into the content of this course is very, very specific, right? But if you step out at the machine learning level, one more step out and look at the level of a solution for a business. Okay, so a firm or a business, its goal is to create value, and typically, let's say, it creates value by producing a product or a service, and in your professional life, whether in the past or in the future, the most important component is not the techniques that we'll see in this course. Okay, in fact, the techniques you may not remember the exact specifics 1 year later, okay, or even 6 months later. What's important is to have a really good understanding, one step in the domain, to really have strong domain expertise, and then mix and match whatever is the suitable solution for your situation, right? So let me mention that. Oh, it's actually not rendering it properly. So okay, so these three components had something to do with how would you architect a solution. I don't know why it's not rendering. Are you guys able to see, not see the right hand side, right? So the right hand side is not visible where there are three more blue blocks.
Yeah, it's blank.
Yeah, it's blank. So I'm trying to see. Okay, interesting. I created the PDFs from the PowerPoints, and somehow it's not rendered properly. Let's see. No, it's not the right one.
We can still see it in the slides that we have. At least I
Yeah.
can.
Yeah. So I was trying to see if I can do that. I can use the browser to do the same thing. So give me 1 second. If browser-based PDF rendering is better, then I can just switch to that. Yeah, I think the browser-based rendering is better. Thanks for the feedback that it works. So I thought it was an issue with the conversion itself. It's not. So let's see. Yeah, so sorry, I'm in the browser. So you can see the three blocks to the right, right? I just need to figure out how to make it a presentation mode. If I make it a presentation mode, I may not be able to see the chat window. Let's see. Oh no, I can. So can you still see the slides?
Yeah.
Yeah, good. Thanks, Avinash. So I need to put the chat on the side. Okay, so the point of this slide is actually not that deep, but at the same time, it actually becomes a big concern. Okay, so if you don't pay attention to it, which is that if you look at the 20,000 feet view is really about, hey, where are we creating value and what is the right solution, or whether it's product or service, and then how do we solve it? Okay, which which includes like how, like maybe it's a cloud app or a SaaS or a standalone product, or it's a physical product or whatever it is. If it involves data and computation, and there's going to be concerns like what computer system, what is the data IO and all that. And then there's a part which is related to actually the techniques, the data science techniques. Okay, and within that there's hundreds of techniques, out of which deep learning techniques are one component. Okay, so what I'm trying to say is that deep learning component of this whole solution that you've built may not be the make and break in the majority of cases. Maybe it is the most important thing for certain specific solutions or businesses, but in general, the technique itself is not the biggest issue. Okay, so you can always swap, let's say, deep learning model with a random forest model and get something working. Okay, so it's just a disclaimer saying that although we're going to be very focused on deep learning models, do have a view of the overall thing that you're contributing to in your team, in your business, or whatever it is. Okay, so with that, let's talk about how does it fit in with respect to the rest of machine learning. Okay, so in terms of techniques, let's say we bucket the techniques into two sets: prediction-based techniques and then exploration-based techniques. Exploration, I just mean unsupervised learning, so clustering, market basket analysis, or anything else like that. On the prediction side is where we're mostly familiar with decision trees, random forests, logistic regression, naive-based classifier, SVMs, and so on. So we might have seen some array of these in a ML 101 course, right? So within the prediction bucket, neural networks and online reinforcement learning could be considered part of this bucket. Although online reinforcement learning also does something more, which is really talk about decisions, and decisions are at the forefront. So you should think of, if you have a toolkit, then this is where the components are getting added. This is what you're going to add to your toolkit. Okay. So let's talk about two aspects to this course that will kind of become apparent as you work through assignments and so on, which is the variety of data. Okay, structured data is something that some of you might have seen. Structured data, I just mean tables. Okay, CSV files, or when you do SQL queries, there are basically tables in a database. So that's what I mean by structured data. So you have ordinal, integer, binary, categorical variables, and so on, right? So deep learning, as you will see, can also be used for such tabular data. And in tabular data, you would think of like a row as a feature vector, right? So you can actually, so if you think of categorical variables, you would do one hot encoding or something, something equivalent. So what deep learning brings to the table is to create vector representations of these categorical variables, okay, the categorical values. And that's going to be something important later on when we talk about NLP. We'll make a connection to this. The second thing which you'll see in this course is that majority of the time we are actually not going to be looking at tabular data. We'll be looking at not unstructured data, what we call unstructured data here. Okay, which is just going to be images, maybe even videos. Although we don't work with videos in the course, but you could potentially work with it in your project. Text, audio signals, and those are all unstructured. Okay, so and graphs, for example, are also somewhat unstructured in a slightly different sense. So with unstructured data, you would ideally want to typically, if you would create features out of this unstructured data and still get a vector representation or a feature vector representation of this data point, right? Like an image. Okay, let's say, hey, this image has some color, some average average density, or some number of edges or something like that. So you can always create features out of an unstructured data object, like an image. Instead of that, deep learning kind of reduces feature engineering effort while processing these unstructured objects. Okay, and we'll see that it'll also become apparent as we go through the course. In addition to data variety, which will be where deep learning shines, and so as I said, in the two buckets, deep learning and online and reinforcement learning. In the deep learning bucket, although deep learning can be used for tabular data, we'll be mostly focusing on unstructured data and text image is what I mean by that. And in the second bucket is online reinforcement learning. It's related to complex decision making. Complex decision making just means that there is no simple transformation from a prediction to a decision. Okay, so for example, if you forecast for tomorrow that it's gonna rain, it's something like a 90% chance it's rain. Your decision to, you can make a decision to take an umbrella with you. Okay? And that's a very simple decision, right? If the probability of rain is greater than 50%, let me take an umbrella. Okay, that's simple. But in most real business cases, the mapping from predictions to business decisions, it may not be that simple. Okay, so for example, how to price products, it's not just based on like raw demand. Okay, there could be cross elasticity or basically some other effects, or maybe your own budget, or maybe many other things, many things that may influence your pricing decisions. Okay, so and in particular in this course we'll be looking at, as I said, decision making is itself a broad area, just like machine learning is a broad area, and we're only looking at deep learning. Decision making is a broad area within which we're only looking at sequential decision making, where we happen to take decisions in a repeated manner. So that's a repeated manner or sequential manner, and that's where online and reinforcement learning ideas come in. Okay, and we'll talk about this in a lot more detail, but I just wanted to give you a sense of these are the two buckets: deep learning for images, video, text, audio, whatever you want to say, and then decision making, and we'll talk about reinforcement learning mostly. Okay, but that's not all of decision making. There are many other ways to decide, but that's what we'll look at. Yeah, I guess this is what summarizes that. Those are two themes: data variety, so new data sets that you probably have not worked with before. Text you might have worked with before when you used, let's say, bag of words or TF-IDF and so on. Here it will be a different treatment. Similarly, images, I don't know if you worked with it before, but if not, here we'll see a treatment based on neural networks. Right? And similarly, within decision making, we'll look at sequential decision making. Any questions here? Okay. So far it's been pretty high level. I'm just trying to get a sense of like, you are going to spend about 16 weeks on this. So what is it that you'll be handling? And what is the type of things that you'll learn? Okay, that's what I'm trying to motivate for a few minutes now. Data variety and complex decision problems, deep learning and online/reinforcement learning is what we'll look at. And of course, it's not completely unrelated. So we'll mix reinforcement learning with deep learning. So it's all, it's all thematic and related to each other. Okay, so now let me give you a few very popular examples. So some of you may already know these examples. If so, if you have some extra information, you can always share. So very popular examples that kind of motivate deep learning. So today, if you look at any science tech-oriented outlets, like media outlets, you'll get so many interesting examples of, or sometimes it's sometimes even hype of what deep learning and modern machine learning can do. Right. So here's one early technical success. Okay, which is in the case of images, okay, vision/images, which is as follows. So ILSVRC just stands for ImageNet Large Scale Visual Recognition Challenge. Okay, it's basically an annual competition that was run for several years by folks from, I guess, Stanford. So it's a visual recognition challenge, and it had several types of tasks, and researchers, folks were asked to build machine learning models which can do something, quote unquote, visual recognition. So different types of visual recognition, and one of them is just classification. So given an image, classify that image to be class A, class B, class C. Okay. So typically these images have a single object, like, hey, here's an image of a human being, here's an image of an airplane, here's an image of an animal. Okay. So it has, in fact, it's a really large scale because the original data set actually has 22,000 categories. and 14 million images. Okay? And this is from 2010. So at that time, you can imagine the scale. Now, also it is huge, right? It certainly cannot fit into your laptop. Will not fit into Google Colab as well. So you really need a dedicated decent GPU to even start thinking about working on this type of a number of classes. Categories are classes. Okay. So one of the tasks, as I said, is just a classification problem. And in fact, it was kind of subsetted so that you only have 1,000 classes, 1,000 categories, and 1.5 million images. Okay, so it's a smaller version of the full data set. And the model that, it's a challenge, and folks were asked to, it's like a Kaggle challenge. Some of you might have done Kaggle challenges. So you basically have to build a model and give it to them. And that model has to predict, what is the class for each image. And the evaluation criteria is slightly different from what you may be familiar with in other courses. So like what you may be familiar with in general. So if you think of a classification problem, you can always report accuracy, right? So how many times did I misclassify? So here, the misclassification is accounted for in a slightly different way. The model is going to predict classes. It'll say what's the probability of this image being human, maybe 0.6%. Sorry, 0.6. What's the probability of this image being, let's say, an airplane? 0.3. What's the probability of this image being an animal? 0.5. Whatever it is. So there's a bunch of probabilities that you generate. It look at the top 5, probabilities that you have generated, which will be the top 5 predictions that you think that this image is of, and then you look at whether the top 5 does contain the true label, okay, the true class of the image. Okay, and so it's a slightly different classification error than, it's a little bit expanded. Okay, it's giving you 5 chances instead of just saying, hey, this is class 1. Hey, this could be class 1, 2, 3, 4, or 5. Let's say out of the 1,000. And given that, you can see there's a lower is better in the plot in the center, and you can see around 2011 to 12 there was an absolute 10% improvement in the models. Okay, so actually the models from 2011 and 2010 were actually using SVMs. Okay, SVMs with a lot of feature engineering. And 2012 onwards, there's an absolute 10% improvement, which is a huge number, actually. And 2012 onwards, most of these improvements have come from deep learning. Okay, so this is one early example, pretty popular. But of course, these days, there's a lot more interesting examples you can find online. Any questions about my explanation about this? Yeah, by the way, feel free to ask any question. There is no such thing as like a bad question. If you have a question, probably some other folks would have it, but of course keep it on topic. But feel free to jump in, add a comment asynchronously, of course, on chat. I'll be keeping a look at the chat.
This is not a question related to deep learning as such, especially what you showed on the slide, but more along the economics of it. How much will it cost to participate in this competition in terms of, say, hosting whatever we're doing on Google Colab?
Google Colab will not work for this. You need, so today you can certainly participate, but your performance will be like this. Okay, you will probably in the 2012 levels. So for 2022 performance levels, it's super hard. You need a full-fledged research lab or a tech company's resources to be able to find a better model. But you can actually do, let's say, the 2012 performance using a commodity GPU on a single machine today.
So, so the only difference between, say, my competition submission versus somebody who has a much bigger set of resources is that they have a much better set of resources.
Resources to search for the best model. So remember, machine learning is all about searching, right? Finding a model, which is like finding a parameters, right? So and the model size, I mean, once you define what model class within which you want to search for the best model, that search process is hard. Okay. And also the current commodity single GPU will have some limit of how big a model it can train. And you will see that 2022 solutions, they may have really a lot more, I guess, going on in terms of searching for the best solution, because they're really, so okay, just to give some more context, this 0.07 that you see here is actually already close to what a human can do in terms of classifying these, like if a human was asked to figure out which one of these 1,000 categories each of the image belongs to, even a well-trained human who understands these 1,000 categories can only do about 93% accurate, okay, or whatever, 0.07% off. So you're really going beyond what a human can do, and for that you just need resources. It's not the size of the model for at least image. The size of the model can fit into a single GPU of today. Okay, like for example, NVIDIA's biggest CPU today has 48 gigs of RAM. Okay, so that's enough to have a vision model easily. It's just that you need time to run and search for the best parameters. That's hard, unlike doing logical regression and stuff.
Okay.
So actually today's challenge is not so much in vision, I think, or maybe at least I'm not super aware of it, but recently over the past 4 years, the big challenges have been in natural language processing, which is where you can't do much on a collab or a single GPU situation in these types of competition. So a similar competition, let's say for text, you really need a multi-GPU, like a cluster type of a setup to do things, yeah, to be competitive. Yeah. Okay, so I guess, is this the same question? So as of today, of all the models used in the industry, roughly how much percentage are DL models is? So, okay, so it's a good question. A big chunk of, first of all, if you are using machine learning, a big chunk of models in non-tech areas are mostly going to be, it depends on the industry. Let's say in finance and healthcare are mostly going to be variants of regression or shallow models like random forest, decision trees, SVMs. Okay. Deep learning is heavily used in, for example, Google of today is actually using some part in deep learning, some part deep learning. All these big companies that you may be using as a consumer, Spotify, Facebook, Instagram, all those things, they are using deep learning in either recommendations, even Amazon, let's say, either recommendations, parsing the text, tagging images, whatever the appropriate tasks are, they're all using deep learning. But then that's a specific, that's like high tech. But the median firms, let's say in finance or healthcare, or let's say even other areas like construction and so on, they are not stuck or anything. I mean, for them, as I said, it's a 20,000 feet view where first the product and the solution should make sense, and then the accuracies, may make sense. And so traditional models are still pretty decently used. And also another quick point is that it's not like there's a big gap between deep learning and traditional models. Towards the end, you'll see that logistic regression is actually an example of a neural network model, okay, without any, what I will say, non-linearity. And we'll talk about non-linearities in the next lecture. Okay, so logistic regression is the simplest neural network model, okay, already. So it's not like they're super different. But I would say in terms of commercially deployed deep learning models beyond tech industry, I think it's a smaller, it's a minority compared to other modeling techniques. I may be completely wrong. So if you find something elsewhere that talks about this, then please share with me, and I can share it with everybody else. Okay, so let's continue with this motivation. So my purpose for the next few slides is just to give a sense of some big wins that happened with deep learning as well as reinforcement learning. Okay, and as again, my slides are not the extensive list. I mean, there are many new things that have happened since that I have not captured here. Okay. So just a quick comment about what happened with that 10% improvement is exactly that, which is the access to GPUs and data. Okay, so this large-scale visual recognition challenge, even in 2010, that amount of data, we didn't have the hard disk. Okay, think of hard disk and RAM and so on. 2005 laptop versus a 2022 laptop, or even a desktop. There's a big difference. Okay, and so with the availability of large data, with the availability of GPUs, things have really exploded. Okay. So let me switch gears and talk about a little bit about reinforcement learning. Here's an example, which is an example in the web domain, and here's the problem is The business problem is basically, here's a web asset, web property, and Microsoft just wants more folks to maybe stay on the web page, spend more time on the articles or whatever it is. Okay, so there's some business metrics here, and the learning component is that you don't know a priori what's the right articles to show to which people, and you don't have a pre-fetched, pre-created bash data. Maybe you can actually even have a bash data, but the problem is you don't know what you didn't try. Okay, so that's the problem that kind of is being solved using online reinforcement learning. So, but to repeat, what is the key aspect that's being trying to be addressed by these online reinforcement learning techniques is that the decision is that you, as a website owner, maybe you have 100 articles show, but the screen size is like, you can only fit like 6 articles or whatever, 10 articles. Which out of this 100 should I show the first time somebody opens, let's say, this msn.com, right? So that's the decision, right? You want to figure out which 10 articles out of these 100 articles. And you also, while doing that, you're making these decisions, let's say, you don't know what would have happened if you had shown a different set of 10 articles. Okay, so that you don't know what would have happened. So you need to do something about this data collection, okay, which is a little bit different. And we're going to talk about this quite a bit when we get to these topics in the second half of this course. Here's an example, right? So anyway, it's the same example, but behind the scenes, what's going on. So user, let's say they have a profile with Microsoft or account with Microsoft. And so they come with their own information, let's say demography or history of what articles they saw and all that. They come in, there's this green box. You can think of this green box. There's some name here, but think of this green box as an online/reinforcement learning solution. Okay, that green box is going to generate, hey, let's show them, these are the 10 articles. Let's show them out of these 100 ones. And then users going to interact with those articles. Maybe they don't like the articles, then you'll get that feedback because you're continuously logging what's happening on your website. Or maybe they'll really like the articles, to spend a lot of time, or maybe or share it on social media, whatever it is. You get some information based on what you took. So these are the decisions that you took, okay, for this user. And then maybe tomorrow again the same user comes, or some other user comes, and some decisions are taken, and so on. So this green box takes into account that the data collection, takes into account that the data collection can hedge against the fact that you don't know what would have happened if something else was shown. Instead of like these 3 articles, maybe something else was shown, then what would have happened? Okay. So that's the key thing that is addressed. One of the key things that is addressed using online/reinforcement learning. So I'll not get into the detail because it's still the first lecture. I just want to give a sense of like some wins. Okay, so this is a win in the sense that when we get to the lecture, they show that they get much higher click-through rates if they do this green box instead of a straight prediction problem. If you just use random forest and figure out what's some articles and just show it, compared to a very straightforward strategy of just using machine learning, this green box gives a relative 20-25% lift, okay, or improvement. And we'll talk about it when we get there. Okay. Next win is from actually 5-6 years ago now, 2016. Which is this game, which is how a RL, a reinforcement learning, RL is I guess the acronym, RL-based agent. Okay, agent just means software, which is called AlphaGo, was able to compete with the then number 1 ranked player in the world, Lee Sedol, and was able to beat the top ranked player 4:1. Okay, or beat the player basically. So before that, no computer software or agent was able to compete with humans in this game. Okay, so there's like the chess situation where in the 90s chess software was improving, and towards the late 90s there was this famous event where chess software could compete with the top player at that time. So similar thing happened here, and behind the scenes the technology is one of the components of technology is reinforcement learning. Of course, there's been improvement since 2016 with now software is way better than humans in this game. Okay, so this game was like humans were best till 2016, but now it's not the case. And behind the scenes there is machine learning and reinforcement learning involved. Yeah, and I guess a very minor point related to that is before that, 2016 event, people, researchers had shown how to play video games. In this case, it's the Atari game. So here is a panel of all the 48 or 50-ish games here. It's just showing, these are just 2D games where now researchers showed how to train an agent, again, a software, a model plus decision making component or a system, which the decisions are going to be joystick moves. And now the software is going to play these games so that it gets high scores. Okay, and they were able to demonstrate such a software. Okay, and we'll in fact implement that as part of your assignment number 4. So we'll see this later. Yeah, so any questions? So I guess again, quickly caveat similar to the 20,000 feet view, you really want to ask whether y% increase or x%, y% increase in classification accuracy, or whether it's a regression accuracy is going to help with sales or revenue or whatever is the business goal. Because if not, then maybe there's going to be you may be prematurely optimizing for something which is not the most important thing for your business or for your product or for your team right now. It's a balancing act to make, but it's it's something to think about, because there's a lot of hype with any new technology, whether it's blockchains or whether it's deep learning and so on. So but in a business context, you want to be nuanced about these things. Any questions so far? Okay, if not, what we'll do is have a quick recap of classification. For many of you who have done an introductory machine learning course or data mining course, this will be a recap. So, and for those who have done it some time ago, please, stop me so that I'm not speeding through this. But it's just a recap of a typical prediction problem, and I'll pick classification as an example. Okay, and then we'll look at a new concept for some of you, which is backpropagation. So classification. So we look at 4 components which kind of constitute a classification task. From the point of view of data, some details about the data, some details about model, the model class which you're picking up, and this model exactly where you can switch between an SVM/deep learning model, okay, or a neural network model. You also need to define like what is the criteria with which you're going to pick or find a model, right? Optimize for the best model on the training data, and so that's the loss criteria or the objective for finding the best model. And then how do you actually instrument it, and how do you actually compute the best model? So that's using optimization typically. Okay. Also, let's briefly look at these 4 components. So data. Actually, even before that, let me just show you what we want to do, right? So at the top is just showing here that given a test example, what does the classifier do? It just assigns one of the class labels to any test example, any new example, okay? And all the training data is used to define the parameters inside this classifier, right? So to design this classifier, you need the training data, the model spec, which model it is, the loss function so that you can define which model is better than another model, and then optimization to get to the best model. So let's talk about data, right? So there are several considerations for data in general. So here I'm just illustrating because I said that, in this course we're going to mostly looking at unstructured data. So I'm just giving a sense of the nuances for just, let's say, image data set, okay, or an image data object. Of course, if you have tabular data, you will have different considerations about, for example, too many categorical values or too many features, or sparse features, missing features, and so on. But let's say for vision, an input could be an image. Okay, so input to your classifier could be an image. And so what is an image? Okay, so let's we're just working through an example of, hey, what is an unstructured data, and this is one example, an image, right? It's not really completely unstructured. It's a bunch of numbers. At the end of the day, once it's represented in a computer, it's going to be a bunch of numbers typically. So An image is nothing. You can think of it as a container which has a bunch of numbers between, let's say, 0 to 255. Why 0 to 255? Why not between 0 to 1 or some minimum and maximum value? That's kind of not super important. Typically, images are just three-dimensional arrays. Okay? So three-dimensional a three-dimensional array or a matrix. Okay, so if you have used NumPy, so just think of having three indices. So matrix has two indices. A vector has one index to refer to any cell. So here you just have three indices to refer to any cell. Okay, so it's a tensor. Okay, so that's what it's called. And although so visually an image can look however it is. As I said, it's a container with a bunch of numbers, which can be indexed by basically three numbers, and that's why it's a three-dimensional array. And the domain knowledge should tell you that the numbers which are there in this 3D array, which represent an image, for example, the image of a cat, the numbers can change. It could be the same cat, and the numbers can change because of many different things. Okay, so here are some examples. So if you take the same picture from maybe 10 feet away, or if you change the light source from left to right, or if the cat moves slightly, or if there's an occluding object, if there's background difference, all these kind of should be ideally the same. We know because we can interpret, our eyes and our minds can interpret this, but in terms of those 3D array and the numbers in them, they could be very different. Okay. So that's something to think about while thinking about models. Now, maybe using a little bit of notation. So just for this review, we'll have typically capital N number of training examples. So think of a data set. If you had tabular data, just think of N rows in the table. X subscript I and Y subscript I will be the feature vector and the label, ith label. Okay, so the 50th row in the table will be X subscript 50 and Y subscript 50. Okay. You may have a slightly different notation in a different course. Don't worry about it. Here we're just trying to say, hey, this is the 10th example, this is the 50th example, this is the 100th example. Okay. And we were talking about images in the last slide. So you can think of xi as the ith image, and yi is the label for that image. Now, as I said, image itself is a three-dimensional tensor. So before deep learning, what you do, you somehow typically you think of feature vector as like a vector, with let's say 10 coordinates and it's one dimension. So what you do before deep learning is to really go from these three-dimensional array or a tensor to some vector, okay, and that vector would be hand engineered, okay. So which means that given an image, you'll create, for example, hey, what's the mean value for the red color? What is the mean value for the green color? How many edges are there, and things like that. Okay, so that's what these names represent here. These bullet points: histogram of colors, histogram of oriented gradients. Don't worry about what they actually don't worry about the technical details right now, because I just want to list that from an image, you want to get a feature vector, typically you would do feature engineering. Okay, it's very similar to even if you had tabular data, sometimes you would do feature engineering by saying, hey, there should be an x square or a log x or a whatever it is for that coordinate, right? So that's what you would do to get a feature vector. But now, as you'll see in lecture 2 onwards, we almost don't do any feature engineering. Okay, so we'll pretty much take that tensor itself as an input to our model. So just brief, commentary on data. Okay, so data is well understood. The moment you have, say, hey, here is an input, here's an output. As long as the input is indexable, and let's say it's a bunch of numbers, whether it's a vector or a tensor, and they have a label, you have the data. Okay, so and of course there's several issues there, potentially missing data and all that, but those are considerations for data. Now let's talk about models, right? So models, there are many models, right? Somebody's saying DL models versus random forest, SVM / logistic regression, all that. There could also be a distinction between parametric models versus non-parametric models, for example, logistic regression, or even deep learning models are typically parametric. It just means that the number of parameters is kind of fixed. Okay, so if it's a 10 parameter model, it's just going to be 10 parameter model, whether you have 100 data points or 1,000 data points. But there are some other models which could be considered non-parametric. Okay, so where, for example, k-nearest neighbor is a non-parametric model. As I said, deep learning or neural network architecture is typically parametric. So you would have a fixed set of parameters, and you also have what are called hyperparameters. And this is something you might have seen if you look at SVM or even ridge regression. So there will be this extra multiplier to the regularizer term, so that you can think of that as a hyperparameter. So these parameters and potentially hyperparameters determine the model completely. Okay, so now let's actually add some notation to a model. And in fact, the model I'm talking about here is actually a linear model. It's a linear model, but I'm not saying it's a linear regression model. It's a linear model. In fact, you will know, if you remember, logic regression is actually a linear model, okay? Because it gives you linear addition boundaries. So let's talk about the notation for a second. The parametric model, I'm gonna so it's not in general, but I'm gonna say, hey, the parametric model F, takes input x. X is just that feature vector or the tensor, whatever it is, and has two parameters, capital W and little b. Okay, and the model is as follows: f of x, comma w comma b is equal to w times x plus b. Okay, so w times x plus b is what? So if you think of really reduce it to simple regression, w is like the slope and b is like the intercept. Right? If you just think of simple regression, x is one dimension, then that's what it is, right? Here, I'm saying x is d dimensions. Okay? Think of x to be, let's say, 2 dimensions. Okay? And let's say we have 3 classes. So it's a 2-dimensional data set, and you have 3 classes. Then w will choose to be 3 cross 2. Okay, so 3 cross 2. So that w times x is 3 cross 2 times a vector which is 2 cross 1 will give you will give you 3 numbers here, and let's say bias is also b parameter is also 3 cross 1, so you will get 3 numbers, okay, from this model. So that's a linear model because you can see this is just a linear equation. Okay, so just a linear transformation of the input. Okay, we'll change the models later. For today's discussion, let's say, hey, this is the model class. Okay, we'll be dealing with. Okay, so since if input, let's say, is 2-dimensional, as I said, and I do three in a 3-class situation, wx plus b should give me 3 numbers. Okay, so what are the 3 numbers? Basically, each number is, you can consider it as a score. It says how, if the score is high, you may consider that, hey, the class 1 score, let's say in the first coordinate is high, you may say that the class corresponding to the first coordinate is probably the right class. Okay. Yeah, which is, let me repeat. So given a model, when we say given a model, which we just mean that we have some fixed parameters, like w comma b have taken specific values, okay, some fixed numbers, and if that f function is our classifier, then our prediction, okay, given the model, our prediction for any new input x will be just this. So you pass x to the input. So you have f of x comma, and you have w comma b is given to you because it's a fixed model. It's already given. So you'll compute those 3 numbers, okay, and then you'll take the argmax. Okay, argmax just means, hey, I got 3 numbers. Let's say the first coordinate is 10, second coordinate it's 5, and last coordinate it's -1. Okay, so 10, 5, -1. So which of these numbers is the highest? 10 is the highest. So what is the argument corresponding to the highest number? Since 10 is the highest, the index of that row is 1, right? So therefore my class is 1. So it's just saying, hey, which of these 3 numbers is the highest? It's the first coordinate. Therefore, let's say it's a class 1. If it just happens that the second number was higher, then you would say argmax would be 2. Okay, the second row is highest. And similarly, if the third row was highest, then you would say, hey, argmax of this course is the third index, and therefore it's a third class. Okay, so if you're familiar with NumPy, then NumPy lets you do argmax operation. Okay, so if you have a vector, you can ask for argmax, and it'll tell you what is the index of the maximum. So that's typically how you do a make a prediction given this model. So any questions about this? So this is an example of a linear model. So if you have seen linear models, let's say even we are talking about classification, so linear regression is not a good thing to bring up right now. Depending on the loss function. Okay, so if I choose the loss function appropriately, then you'll see that this is actually corresponds to, for example, a lossy regression model. Okay, or if you choose the loss function slightly differently, it will correspond to SVM. Okay, we'll see that in the next slide. So what have we done so far? We have looked at data, and data was nothing, this is just a vector and a label for classification setting. And we talked a little bit about images. Next, we talked about models. And in particular, I didn't want to talk about all sorts of models. I said, hey, there are different types of models, parametric and non-parametric. We think of a parametric model. Here is an example. This is a linear model. It has two parameters, W and B. Okay. You can also combine it, combine W and B and say, hey, there's one parameter, which is parameter set, which is a W comma B. You can say that pair can also be called a single parameter. But W and B are the parameters. And how does the function look like? Here is a complete expression of how the function looks like. If given an x is first multiplied with the matrix W, and then a vector is added B, and then you get 3 scores. 3 scores, why? Because in the running example, I said, hey, there are 3 classes, and x's input data is 2-dimensional. So that's where we are. And I want us to take a brief 10-minute break, and we'll come back at 5:05, and then we'll recap loss function and optimization. Okay. So I'm going to pause recording now and take a break and come back at 5:05. Yeah, so everybody can see my slides again, right? So if not, just let me know over chat or via voice. So we're going to continue where we left off. So what I was trying to say was that we saw in the previous slide is just a linear model definition. Okay, so this is how you could define a model. And the reason why I'm defining it in this way is actually because you will see that I'll make a connection to neural network model, which is a feed-forward neural network later on. Okay, so let's now define the loss function, right? So the loss function should take as inputs these scores that is being provided, these scores that are being generated by this function, right? So remember our example, X was 2-dimensional and we had 3 classes. So we're producing 3 scores. Hopefully higher score means that's the class, that's the most likely class for that example. So F is basically, think of this as F as a 3-dimensional vector, 3 numbers, okay? And let's say each number is represented by Sj, okay? S1, S2, and S3. Since there are only 3 numbers. Now, given SJs, you can now define a loss. So loss generally has a couple of components. One of the components is going to be completely defined using training data. Okay, so which means that you will have both the X and Y together determine what the loss is, Xi and Yi, and in fact, Xi and Yi over the full data set. So in particular, this L data term, which is a loss, it's basically a sum over each individual observation, each individual example in the data. So okay, so if there are n examples, then capital N examples, which is like let's say 100 examples, then it's a sum over 100 terms. Okay, so and each term, let's call it the ith term being capital L subscript I. Okay, so that's the ith term. So here are some 2 specific examples of what this ith term is. And depending on that, you actually get logical regression or potentially an SVM. Okay, SVM model. So let's only focus on the logic regression model for now. So how do we define Li term? Okay, as I said, to define the loss, we'll use both the feature and the label. Okay, so the way we'll define it is that, hey, for the ith example, we have Yi is the true class. Right? Yi is a true class. So we said we have 3 classes. class 1, class 2, class 3. So yi would take value 1 or 2 or 3. Right? So let's say that's the class label. Then the loss is the negative log of a term which we're calling as conditional probability. Conditional probability of yi. So conditional probability of y equal to yi given x is equal to xi. So negative log of this probability. And what is this probability that's given in this bullet point here is equal to a expression which is like e to the power sj divided by sum over e to the power all the scores. Okay, so remember there are 3 scores, 10, 5, and -1. Okay, there are 3 scores, 3 class classification. So let's say we also said that let's say the first class is the true class. Then the loss for the ith example will be negative log of this probability. And what is the probability? It's e to the power, what is the true class? The true class is the first class. So e to the power 10 divided by e to the power 10 plus e to the power 5 plus e to the power -1. Okay, so the probability is equal to that ratio, and then negative log of that ratio, that probability is the loss. Okay. So although I've defined it this way, okay, and this is not probably the way you saw how logistic regression, or in particular multi-class logistic regression, is defined, it turns out to be the same thing, exact same thing. There's no difference in multi-class logistic regression treatment that you've seen elsewhere and what I'm saying here. Okay, so this loss, the reason why I wanted to define it this way is that this loss, Li, is also called the softmax loss, logistic loss, or the cross entropy loss. Okay, so several times you might see, in fact, in the packages that we'll use later on, like PyTorch, they will use cross entropy loss as a way to call that function. Okay, that function would have implemented behind the scenes just exactly this. Okay. Any questions about this side? So don't ignore the SVM loss for a second. So I'll just focus on if there are any questions about this Li term. Okay, so if there are questions, do add it in the chat. As I said, no question is typically a bad question. So ask if you have something, if you don't understand, ask me to repeat as well. So that's fine too. What I want to say now is that loss generally has 2 components. One is completely determined by data, and the second part typically is determined by your preference, and typically it's called regularization. Your preference or some domain knowledge, and that's called regularization. Okay, so why do we have the second component, which doesn't depend on the data typically? Why do we have that? It's just because we prefer, maybe there are multiple models which all do really well on data. You want to pick the model which we prefer. Okay, maybe, and that choice, for example, you want a unique model, we have a desired model, a certain type of model which has a lot of coefficients 0 and some coefficients 1, things like that. Okay, so it's to kind of avoid overfitting into the just data, only believing in the data and not ignoring the domain knowledge. Yeah, there's a question.
Yeah, Professor, this loss function, is this same as impurity or diversity that we have studied, like entropy, Guinea square, and
yeah, it looks like that. So it's not exact. This is not the definition of entropy. Oh yeah, okay, good point. So not this softmax expression, but the negative log of probability is related to entropy. Yes, and cross entropy is exactly is exactly that. So let me actually, it's a good question actually. Let me just switch over to a text. So hopefully everybody can see. So entropy. Okay, so entropy of a typically random variable is, not even put space there, is the sum. Okay, sum over I. So there's a minus sign there. Log of the probability of x is equal to xi. Sorry, xi. So let's say not even put, let me put not even xi. So let's say x is a random variable. Sorry, the sum over I, p of probability of x is equal to I times log of the probability of x is equal to y. Okay, so and there's a negative sign in the front. So this is the definition of entropy. Okay, so this is like, so think of, if let me just give an example. So X is a binary random variable. So random variable. Okay, so let's say heads or tails, right? And let's say it is actually unbiased, which means that it's a probability of heads is equal to 0.5, which means probability of tails is 0.5. So what is the entropy? What is the entropy of this random variable? Right. So this is just negative sum, and the sum, there's only two values that X can take, heads or tails. So for each one, what is the probability? It's 0.5 times the log. So by the way, log is log to the base 2. Okay, so log of 0.5, right? Again, minus 0.5 times log of 0.5. Do everybody agree with this? There are only two times, right? So two values. Or any questions about this? I want to not confuse anybody. So this is entropy, right? And this, the two terms, so 2 times that. So minus 2 times 0.5 is just 1. So minus log of 0.5, right? So 0.5 is actually 1 by 2. And so if you remember log arithmetic, some formula, some properties that log satisfies, it's just log of 2. Okay, so minus and 1 by 2, they somehow you can reduce it to log 2, and this is equal to 1. Okay. So entropy of this random variable, binary random variable with equal probability heads and tails, is 1. Now let's talk about cross entropy. So cross entropy, the reason why it's called cross entropy is exactly, almost looks like entropy, but it's between ground truth label versus what we are predicting, predicted probabilities. Okay. And that's why it's it looks messier. So by the way, previous example has nothing to do with prediction or machine learning. It was just a simple example of what entropy is, and you can use that for node impurity definition and for doing splits in addition tree, right? I guess that was what motivated your question. Now, cross entropy is very similar to entropy. It's the same idea. So the way you think about it is think of two random variables. Okay, so all of these are, I'm just saying it's a ground truth label and predicted probabilities. Just think of them as two random variables. By which I mean, hey, if ground truth is label 1, okay, so class is 1. Okay, so ground truth label is actually 1. Let me just is label 1. Then the way you think about it is, hey, you have two vectors, which is 1, 0, 0. That's the ground truth. Okay, so first, since it's label 1, the first coordinate is 1, the second coordinate is 0, third coordinate is 0, and the second vector, is a second vector is going to be the probabilities. Okay, what is the predicted probability of it being class 1? So maybe you're saying, hey, predicted probability of class 1 is 0.7, predicted probability of class 2 is 0.25, and this is also 0.25. Let's say it's actually 0.5. So these are three predicted probabilities. They sum up to 1. Either you can be class 1 or class 2 or class 3, so they have to sum up to 1, and that's what the softmax expression is doing. So this is predicted probabilities vector. This is the ground truth vector. Now cross entropy is just saying, hey, you have these two vectors. The way you take entropy is basically exactly follow the entropy definition here. Okay, follow the entropy definition, but you take sum over not t of xi, but whatever this vector is at the ith location. Okay, so you can see that ith location is 1 only for the first coordinate and 0 for the other two coordinates. So the sum actually just vanishes. Okay, and so cross entropy just becomes minus ground truth label, for the first location is 1, and so it's minus log of the probability of whatever x is equal to class 1 or whatever. Okay, so that's cross entropy. So let me actually go back to the slide, because this will give you a little bit better understanding of that. So if you look at this minus log of the true class. So whatever was the true class, what is its probability that you're predicting? That's what it is. Because why is it the true class? Because yi we know is a true class in the training data. Okay. So what is the probability you're predicting for that class? Maybe it's yi is class 1, then what is the probability you're predicting for class 1? And that's the only thing that is accounted for in this loss. Okay. Okay. And that's why it's cross entropy.
So, Professor, we can say that we are dealing with the cross entropy with the two type of distribution, right?
Yeah, you can think of two types of distributions. Yes.
Yeah, and in entropy, we deal with the one type of distribution, either it's a normal distribution or any kind of distribution, right?
Any distribution. Yeah. So this whatever the connection, whatever these probabilities are. Yeah.
Okay.
So just think of entropy by the way, at least in the vanilla version, is only defined on discrete distributions, as in like heads or tails, or 1 or 2, 3, 5 outcomes or whatever. So yeah. So don't bring normal into the picture, normal distribution in the picture. But yeah, you're correct. I was gonna say one more thing. What was that? Oh yeah. So okay. So another intuition. So if you didn't see the, so you saw the text I was writing on the notepad. If that was not very intuitive, which is acceptable, you can go back to the lecture later. I want to give you an intuition of why this makes sense as a loss. Okay, so forget about all this, relation to logic loss and all that. So why does this make sense as a loss, right? So if you know what the true class is, okay, ideally you prefer that the true class's probability that the model is predicting is high, right? Ideally you want to say, hey, if the true class is yi, my score for the true class should hopefully be high, right? Or this probability that's computed from the model should be high. If that is high, then the log of that probability, okay, is going to be less negative. Okay, so by the way, probabilities are all between 0 to 1. So log of a number less than 1 is generally negative. Okay, so for example, log 0 is minus infinity. Okay, so log of, so if hopefully probability is high, so log of probability high in the sense of close to 1, hopefully, therefore log of the probability is less negative, and the minus of that less negative just means small positive, whatever it is. So you don't, so your loss is small as long as you predict a high number for the true class coordinate, so for the true class. Okay, and similarly, if you predict although the true class is with the class 1, you say, hey, probability of class 1 is almost 0, then log of that almost 0 is going to be a huge negative number, and in front of it there's a minus, so huge positive number. So the loss is high because you predicted for the true class a very low probability. Okay, and we are saying it's probability, but that's just a transformation of scores. If the score is high, probability is high. If score is low, probability is low. Okay, so it's just no confusion there. So you can interpret, hey, this loss makes sense because it's saying, hey, if you don't predict the true class, you're like, your loss is high for that example. Okay. But good points from students. So let's actually talk about regularization. As I said, regularization can have various motivations, and typically it enters as a second term like this. So you generally have data term like squared loss or loss across entropy loss, plus lambda. Lambda is just to think of it as a multiplication factor, like a number like 10 times or 0.1 or 0.01 or whatever. And then this regularization, typically it's a function of the parameters. It's not a function of the data. So it could be like, for example, the 2 norm of a vector. In the linear regression, ridge regression case, it's the norm of the, or the sum of the squares of the coefficients, okay, of the model, right? So in fact, even for these two parameters here, W and B, you can have a very similar interpretation. In fact, L2 regularization, or the ridge type of regularization, is just the sum of the squares of the entries of the matrix W. You can have a very similar thing for the B parameter as well, but typically you don't see such a regularization for the B parameters because B is not even interacting with the data, right? It's WX plus B. So W is the one which is like scaling up and down the X. So generally you would have a regularization on W. So L2 just means sum of the squares of the entries. L1 regularization just means sum of the absolute values of the entries. That would be called lasso regression. And elastic net just means some sort of a combination of those two. So this is examples. Examples of regularization. Later on in deep learning, we'll see there could be some other types of regularization. We'll see what is called dropout in like third lecture or fourth lecture. Okay, we'll see something called dropout. Okay, so that was about model. That was about loss criteria. Just wanted to give you like a recap of course, you might have seen some other types of loss, or sometimes you wouldn't have explicitly thought about loss when like somebody is discussing about logistic regression. They wouldn't have explicitly talked about loss, but this is how you can think about it. Like, hey, here's the model, here's the criteria, cross entropy criteria. Now what you can do is like plug and play. So you can keep the loss criteria the same, cross entropy loss, but you can change the models now. Instead of logistic regression model, instead of a linear model, you could have something else. Okay, whatever produces scores, as long as you can plug it back into that cross entropy expression, then it's a criteria to define, criteria to that can be used to search for the best model. Okay, so how does optimization consideration look like? So I just want to put all things together. So you have parameters w comma b that enter into the regularizer, and regularizer is multiplied by some, typically some number like 1, 10, minus 1. Sorry, not minus 1, but 0.1, 0.01 or something. Okay, so it's just a scaling number, and then that feeds into the overall loss. Okay, and similarly, all these examples together. So the features are input into our model, which also the parameters go into the model, and that together with the labels determine the data component of the loss. And so this L is the sum of both regularizer and the data component. Okay, and how do we and in general, like instead of w comma b, you can think of theta as a stand-in. Theta is this Greek letter. Just to say, hey, in general, there could be parameter theta, and so theta enters through regularization, theta enters through evaluation of like something like cross entropy terms, and eventually there's an overall L, which is a function of theta. Okay, so theta is generally considered a parameter. Gamma is generally, you can say it's a hyperparameter. Okay? There could be many other hyperparameters, but this is just an example. And so we'll not spend much time on optimization, but at least right now. But the optimization approach we'll take is that we'll kind of focus on what are called differentiable models. Okay? So differentiable models just means you can take a derivative. Okay, like you can take a derivative of the model. So if you remember, model is just a function. Okay, so f is equal to wx plus b. Now we'll look at, so that model is actually a differentiable model. Okay, so we can take first derivatives, for example. In particular, we'll look at what are called first order methods. If you don't want to use the word, just think of, we'll focus on gradient based methods. So what is a gradient? Gradient is just a vector of partial derivatives of a function. Okay, so let me actually again go to that and say, so partial derivative. So let's say f of x is equal to x square. So let's say I wanted to use two notations. So x. Okay, so x1 square, okay, plus x2. Let's say f is x1 comma x2 as the input. So this is a function of two variables, x1 and x2, and it's x1 square plus 2 times x2. Okay. Then what is the gradient? So gradient of this function f with respect to its inputs. Okay, there are only two inputs. Okay, so gradient will be again two-dimensional because there are two inputs. Is going to be equal to, hey, what is the derivative of the function with respect to what is the partial derivative of the function with respect to x1? Okay, you can see that that is 2x1, right? Right. I mean, if you have a square, then the derivative with respect to a is like 2a, right? So it's 2x1. And then what is the derivative of this function with respect to x2? Okay, that's 2. Okay, so this is the gradient. Is the example here? It's the gradient of the function with respect to its inputs. Okay, so the gradient is just a vector. Just think of it as a vector whose so its dimensionality is the same as the input to the function. So if there are two inputs, of course, the input is two-dimensional. Gradient is also two-dimensional. It's just each coordinate is just hey, how much does the function vary if I vary one coordinate of the input? Intuition, that's what it is. Okay. let me switch back to the slide. Yeah, so it can be, so this gradient actually can be computed numerically. So as I said, if you slightly change one coordinate, let's say for simplicity, z is only one dimensional. Okay, so input is one dimensional. So it's just saying, hey, if you slightly change input by a little small quantity h, then how much does the output change? So that rate of change is called is a gradient. So in one dimension, that's the derivative. In two dimensions, it's just the partial derivatives. Okay. So you can actually do that, compute the gradient analytically, and that's what we did in that notepad. Okay, so we said, hey, if you have 2x squared, then the gradient is 2x. And we can also use chain rule, which is like, for example, if you have x to the power log x, okay, then how do you find its gradient with respect to x? So you can actually now say, hey, let's, instead of log x, let's call it y, then it's x to the power y. Then how do you take its gradient? So there are some rules that you can follow from basic calculus to figure out what is the rate of change of this function with respect to x. So why did I introduce gradient is because in optimization, we will be only looking at a very narrow area of optimization, which is gradient-based methods, because our models, and you see most deep learning models, will be differentiable. Okay, and so we'll use gradients as a way to find the best model. Okay, so we have the loss criteria defined. We know what type of models we want to work with, linear models or whatever deep learning models later. We just now want to figure out how to find the best model. Okay, so loss is defined, models are defined, model class is defined, but how to find the best model. So the optimization approach or the computational approach we'll follow is called a gradient-based strategy, where you start with some model parameters, some candidate numbers. Okay, so let's call it W0, P0. Okay, so some arbitrary matrix, so some matrix with some arbitrary numbers, and some other vector with some arbitrary numbers. Remember in a running example. So clarifies the question, do we have to do any of these calculations manually? No, but it's good to know behind the scenes what's happening. So you don't have to do any of these calculations, at least professionally, no. Even in the assignment, I don't think there's anything like this. Yeah. But the strategy is important. Okay, so what is a gradient descent-based strategy or gradient-based strategy? Is that you start with some candidate parameter value, and then say, hey, what is the loss at the current parameter? Because that's some, if you put W comma B naught, some loss would be like 10 units. Then you'll say, hey, what is the gradient of this loss with respect to parameters? Okay, with respect to these parameters, W naught, B naught. In general, with respect to parameters, evaluated at W naught, B naught. Okay, there'll be some gradient value. Okay, so and that you will use that gradient information and the model parameter to update to a new model parameter pair. Okay, so actually I'll show you in the next slide probably. So basically what you're trying to do, the intuition for this type of optimization technique is you start with a old or current parameter value, you somehow compute the loss itself and the gradient of the loss with respect to the parameters, and then you'll see a simple way to update to a new set of parameter values. Okay, so then you keep repeating this iteratively. So it's an iterative procedure. You go from W0 B0 to W1 B1 to W2 B2 to W3 B3 and so on. And eventually you'll hopefully get to good parameters. Okay, so all the magic lies in, hey, how do I go from W0 B0 to W1 B1? You kind of use the gradient as information to improve yourself and find a better model. Okay. Yeah, let's actually see. Yeah, so what exactly is the update step, right? So we'll talk about, actually, yeah, we don't even have to talk about batch gradient descent. So gradient descent is what we saw in the previous slide. Batched is an idea which just says, hey, this gradient of the loss, this gradient of the evaluate L, right? So L is a function of all the data set, that all the data points that you have. Remember, L had regularizer and also L data. And L data had like the sum over all my data points. So if I had 100 examples, it will sum over all 100 examples of each individual example's loss, right? So batch gradient descent just says, hey, instead of all the 100 examples, take only 10 examples, okay, to compute the loss. So why 10 examples, or which 10 examples? So what people do is, it depends on the variation of how they want to define the iterative procedure. But batch just means take a smaller set of training data than the full training data that you have to define the current loss. So of course, that current loss will not be the same as the full loss that you could compute when you had used full data, but it's like a proxy. It basically saves some computation. Okay, so that's what batch is. And in particular for the model that we were talking about, the 10% absolute improvement in ImageNet large scale visual recognition challenge, that used a batch of 256 examples out of the 1.5 million examples to do that iterative step, to compute the loss and compute the gradient and all that. Okay. But what exactly is this gradient step? Okay, so it is as follows, right? So you get the gradient of the loss with respect to parameters. Okay, so that's with respect to parameters. So you'll have a grade. So that's represented here. Okay, so gradient of the loss with respect to parameter W is represented here. Gradient of the loss with respect to parameter B is represented here. So this, inverted triangle subscript and L just means the gradient of the loss with respect to that subscript parameter. Okay, so the update is very simple. So it's just saying new parameter is the same as old parameter minus, it's an additive, it's a subtraction minus some constant. Okay, so this is like a number, let's say 0.5, 0.01, 0.1, whatever it is, times the gradient of the loss with respect to the parameter. And this is where the dimensionality makes sense, right? So if the parameter was 2 dimensions, if let's say W were happened to be 2 dimensions, then the gradient of the loss with respect to the parameter will also be 2 dimensions. So it's like a 2D vector minus a 2D vector with some scaling here. Okay, these scalings are in fact have a nice name. They're called step sizes or learning rates. Okay, so learning rates because they help. If they're chosen too small, then you take a lot of iteration to get to a best model, to learn or find the best model. But if you choose step size or whatever, this learning rate too large, then you may quickly get to something, but then because they are large and this is an iterative procedure, you may oscillate or something like that. Okay. In fact, I think next page has a figure. So what is gradient descent or this optimization procedure? I mean, we're just getting a sense of like what is optimization here. So think of this is a one-dimensional picture, so it's really an illustration. In reality, even for logical regression, you can't really visualize it like this. For deep learning models, you can definitely visualize it like this. For logical regression, the loss curve, even in illustration, should not look like this. Okay? It will generally be only like it'll look like a ball. Okay, so it will not have this extra second ball. Okay, it will only have one ball. So for logical regression with cross entropy loss, which actually defines logical regression anyway, you can only go down to the bottom to the best model. So what is the y-axis? The y-axis is the here it's not really loss, and that's why it's a negative value. But y-axis you can think of as like a loss term, or something that you want to minimize. Okay, and x-axis is the parameters. So is the range of parameters. Here in this illustrative example, is just a one-dimensional parameter here, and y-axis is also not loss. But what we want to show is how does gradient descent, why does gradient descent make sense? So what happens is you start from some place. Okay, so for example, think of this blue dot here on the left side of the valley. If that's the old parameter, so that's the old parameter, let's say 0.5 or something, then the gradient, when you add the gradient to this 0.5, the gradient, when you subtract the gradient minus alpha times the gradient, that 0.5 will be like 0.5 minus something. So it will go towards the left. And that's why in the loss curve, you will go down. Okay? So it will say, hey, go to the left. If you happen to be over here, it will say, hey, go to the right. Okay? That's what the gradient descent procedure will say. Okay? And how am I interpreting that? I'm just saying that if the current value is, let's say, 0.5, which we were saying in the next slide, it'll just say, hey, do a subtraction of minus 0.1. So if you are at 0.5, do a subtraction of minus 0.1, you'll get to some other dot here. And you'll again subtract, potentially you'll get somewhere here. But if you overshoot, then it'll say, hey, come back, go to the right. And that's what gradient descent is. Okay. For logical regression, you can get to what is called like global optima. So there's only one best model, or at least they're not two competingly, two very different regions with best models. Like it's going to be like one valley. Okay, that's kind of a global Optima situation. But with deep learning, actually, and this is one of the biggest problems or biggest differences of deep learning with, let's say, some of these models like linear models and so on, is that there are many valleys. Okay, so there's many hills and valleys. Like if you think of these curves as going up being hills and going down being valleys. And so gradient descent can only get to local optima. Local optima means like locally into a valley. Okay, because remember, we're minimizing loss, so we want to go down and minimize loss. But that loss may not be the lowest. It could be some, there could be some other place which have the lowest loss. Okay. Yeah. Any questions about gradient descent? Yes. No questions. Okay.
Professor, I have a question.
Yeah.
So is there a way we can find out like which minimum is global or which is local?
Computationally, no, because both look the same. If we had a way to computationally figure out efficiently, so efficiently just means, of course, you can always try out everything that's possible in the parameter space and figure out what is the global optimum, but that's not possible. Okay. But if you just do gradient descent, yeah, you will not be able to know because both look the same. So what is happening at the bottom of these valleys? Okay, at the bottom of the valleys, the gradient is 0. Okay, the gradient is 0, so you don't change the parameter. So it's like saying, hey, the old parameter is let's say here it's 0.3, and then the gradient is 0, so the new parameter is also 0.3. So you're not updating anyway. It's like a converged thing. Okay, so but coming back to your question about can we differentiate global versus local by just while doing gradient descent? We cannot.
Okay.
So, Professor, our aim is to go for a global minimum.
Ideally, yes.
If we lie somewhere between a local minimum, then how we will approach to the global minimum? Suppose if we lie on the second blue point, that is right side of a loop.
First of all, we won't know whether it's local or global. Okay, so let's say it was local. How do we jump to global? There are some computational procedures that do that, in the sense that they, these are all, I would say, rules of thumb or heuristics. Call it. Hey, we are at some point. Let's randomly see if there is any other point, maybe in a certain region around me where I can further reduce loss. There's some rules like that you can try, but in general you cannot.
Oh, thank you.
Unless you actually spend a ton of time and explore every possibility in terms of parameters, you would not know. Yeah.
Great.
Okay, so I'll skip tuning of hyperparameters because it's related to cross-validation. And you'll see in deep learning, we don't do much of cross-validation, if any, because of huge computational costs in general, even to train, even for one configuration, even for one hyperparameter choice, to train your model takes a ton of time. So we don't spend too much time on hyperparameter tuning. And so I'll skip the cross-validation idea, but it's also an idea about optimization. Right, but it's not just pure optimization like gradient descent on training data. It's related to like trying to guess a sense of generalization by holding out one fold and like training on other folds and so on. Okay, so, but if you have questions about cross-validation, we want to recap, come to my office hours or TS office hours, and we can discuss. Okay, but this just kind of wraps up our review. So today's objective with this part at least was just to kind of get ourselves familiar again with some things that we've seen before, typically. I guess, so some of you have done 572 and 575. So basically data, considerations about data. Hey, how big is the data? How does the format look like? What is the model choice? Is it a linear model? Is it a random forest model? Is it something else? What is the loss choice? For example, regression, you would have a squared loss choice, for example. Or here we saw cross entropy as an example choice. And the reason why I use that is because in deep learning we'll pretty much be using the same loss throughout. So I just thought that's why I wanted to do that. And then last part is optimization. although we'll be using software, and so as Khalifa asked, we don't have to do gradient descent by hand, but in the first assignment, you will do a little bit of computation. I mean, not manually in the sense that not like multiplying matrices and so on, explicitly on pen and paper, but you will be using some ideas about gradient descent explicitly while you solve assignment 1. Okay. So those are the 4 parts. And what I want to do is actually briefly get started on backprop. Okay. So any questions so far? So are we supposed to build these models? So we haven't seen any model yet. So we're going to look at, so there's an example model, by the way, if you're concerned, hey, it is getting too complicated, we will not be looking at, we have to define the model. Okay, that much we certainly have to do, like what is the model? But training the model behind the scenes, it's going to be gradient descent most of the time. And we don't have to write that low level code. Okay, so let's actually, let me give you a sense of like, what does that code look like? Linear classifier, right? So what is a model, right? So here is W and B, for example, right? It's actually, so this code is actually more verbose because we are explicitly saying what the loss is and what the gradients are, and we're actually doing a gradient step. Okay. And this is actually part of the assignment, by the way. But in general, let's look at something else. I don't know if any of these are a quick example or not. Okay, let's actually, sorry for the text, but let's actually directly get to the model. So this is how you define a model. Okay, so we have to build this model from scratch. Khalifa, you're asking, so means you need to at least define something like this. Okay, this will at least say, hey, given the input, what am I going to do with it to produce these class labels or to produce these cores? Okay, so that much you have to do, and that's going to be, that component is going to vary from, let's say, application, but the remaining parts, training loop and all that, they will be pretty much the same everywhere. And you don't have to do it from scratch every time, in the sense that if you define that loop once, you can kind of reuse it other places. Model also you can reuse, certainly, like this model definition can be used elsewhere as well. But you have to define, when you say build these models, you have to at least define it and then train it. For your assignments, you will certainly not doing things from scratch. For example, assignment 1 and 2, you'll be starting with some starter code and then modify, play around, tinker. Okay, so you're not being thrown into the ocean without knowing how to swim. So you will slowly ramp up, and you will have starter code for questions which where you'll have to train these models.
Professor, are we using PyTorch or TensorFlow?
We happen to use PyTorch throughout, yeah.
Okay.
Except for the first assignment where there's a component which requires you to use Keras. Keras is a specific subset of TensorFlow, so it doesn't really expose TensorFlow details. But yeah, we'll mostly be using PyTorch from assignment 2 onwards. Assignment 1 has a brief component with Keras, which is part of TensorFlow. Okay, so let me come back to backprop. So backprop is just talking about, so the reason why we're introducing, so what's the goal for this part, right? So goal is, how do we compute these gradients? It looks messy, right? So how do we compute this gradient of a loss with respect to parameters? Computers do it automatically today. Okay, so in PyTorch or in TensorFlow, as somebody commented, there's actually behind the scenes this gradient computation going on. What is the gradient? Gradient of the loss with respect to parameters, because you need it for doing these updates, right? Doing this iterative procedure and finding the best model. So you need gradient computation to do gradient descent, and gradient computation is achieved using backprop automatically behind the scenes in these softwares, okay, using PyTorch and TensorFlow. But it's not magic. Okay, so the objective of this section is just to say, hey, backprop is nothing but chain rule. Okay, chain rule, and we'll look at that in a second. So what I want to do is directly look at an example first, and then go back to the 2 slides that I just to generalize it. Okay, so what is backprop? Let's understand it through an example. So let's say we have a function like this, g of a, b, and c. Okay, it's a simple function. It's a times b plus c. Okay, so of course, if given any three inputs, you can compute what a times b plus c is. Right? A, b, and c are, let's say, numbers, arguments. Okay, this is a three-dimensional function. So what we do first is like what we do as like what computers do is represent this function as a graph. Okay, as a graph of some elementary computations. So you can see, hey, so what is a graph? Graph is just a collection of nodes and edges where nodes represent the elementary computations in our case. Okay, and edges are just connecting those nodes. So for example, A, B first get multiplied, and you can see that this node is like a crossed up. And then whatever the result is that is passed on, and C and that result together come together and they get added up, and then that's the output. This is a very simple idea. And by the way, this is what happens behind scenes. So you need what is called a computation graph. It's just a graph with some nodes representing computation and edges representing intermediate results. Okay, inputs are intermediate results or output. Okay. So we draw the graph, and now let's talk about how would we come. So and so what is our goal? Our goal is to find the gradient of, let's say, any function. In general, loss function with some parameters, but hey, let's start with this function. What is the gradient of this function g with respect to a, b, and c? Okay, that's the question. Now, even without doing this graph, you can directly say, hey, what is the gradient of g with respect to c? Okay, that's 1 equal to 1, right? So you can literally say, what is the gradient of g with respect to c? It's 1. What's the gradient of g with respect to a? It's b. And what's the gradient of g with respect to b? It's a, right? So I hope we agree on that. But we'll see a computational way to do it, which can be expanded, which can scale to any arbitrary graph mechanically. Okay, you won't do it, but behind the scenes, the computer will do it. Okay, the packages will do it. So the way we do backprop is to start from it's a computation graph. It's a directed graph. So you can see there is arrows. So computation is going from left to right. So we start from the final result. So what is the edge which corresponds to the result, output, g, right? So g, let's say we start with the initial case, gradient of g with respect to itself is equal to 1. Okay. So gradient of g with respect to itself is 1. And then what we'll do is compute the local gradient, okay, so local gradient of the output of this computation node with respect to its input. Okay, so let's call this edge h, this edge at the top, and this edge is c. So this edge is a, this edge is b, this edge is c, this edge is h, and this edge is g. Okay, so this is an addition node. It has two inputs. So what is the gradient of its output with respect to its first input? It's equal to 1. What is the gradient of this? What is the gradient of this output with respect to its second input? It's also equal to 1. Remember, if you're adding two numbers, what's the gradient of that output with respect to any one of its input numbers is equal to 1. Okay, and so that's the local gradient, what I'm calling as local gradient. So you have local gradient, two local gradients which are equal to 1, and then you have an incoming gradient which is equal to 1. It's a base case, so gradient of g with respect to itself is 1. With those two gradients, we're going to pass backprop as we pass it back to any previous computational nodes. Okay, so here we'll take gradient of g with respect to g times gradient of g with respect to c, which is equal to 1. We'll pass it back on the c line. In the c edge, there is no other further computation needed. So gradient of g with respect to c is equal to 1. Okay, that was known before, so there's nothing much going on. So let's talk about what's going on in the multiplication side. Okay, on the multiplication side, let's look at the multiplication node only. Its output is h, its input are a and b. Okay, what's the gradient of h with respect to a? It's b. Okay, what's the gradient of h with respect to b? It's a. Okay, these are local gradients again. So it's just what is my output? If you think of in terms of the multiplication node, my output is h, my input is a. What is the gradient of my output with respect to input? That I can compute, that is equal to b, right? So what I can do is with this local gradient, I can multiply with the incoming gradient, which is gradient of g with respect to h. Okay, multiply them together. Okay, so if you see gradient of h with respect to a times gradient of g with respect to h is b times 1 is equal to 1. Okay, and now you can think of informally you can kind of cancel gradient of h in the numerator and gradient of, so partial derivative of h in the numerator and partial derivative of h in the denominator, and you can get the gradient of g with respect to a. Okay, so that's chain rule. Yeah. So you multiply this with respect to this. That's chain rule, right? So and so we got the gradient of G with respect to A, so with respect to A, which is B, and gradient of G with respect to B, which is equal to A. Is the chain rule idea clear? So what we're doing is there's some local gradients that we're computing, and there's some incoming gradient, and we'll multiply those two and pass it back all the way to the input. So we're starting from the result. First, we compute the local gradients here, multiply with the incoming gradient, pass it to each branch, each input that is coming to the addition node. There's nothing happening on the C edge, so that's fine. We are done. On the H edge, we still have to compute the local gradients, and those are B and A. Multiply with the incoming gradient of G with respect to H, and that's equal to 1. And then you'll get the gradient of G with respect to A, gradient of G with respect to B. Is that clear? Okay, let's actually look at another example. I won't go into all the black, annotations here, but let's focus on this red box here. So that red box is trying to show this function. Okay, this function which is in the first line, 1 by 1 plus e to the power minus ax plus by. So this function needs four inputs to compute whatever is the output, right? A, B, x, and y. So A, B, x, and y are on the left hand side. Okay, they are the inputs. Okay, the output is G. Okay, so what we want to compute, by the way, our goal is to find the gradient of G with respect to its inputs. Okay, gradient of G with respect to A, gradient of G with respect to x, gradient of G with respect to B, gradient of G with respect to y. Okay, and I'm also giving you the current values of A, B, x, and y. That could also be needed. Now, again, the backpropagation idea is let's pick nodes. Okay, let's compute the local gradient. Okay, local gradient is G with respect to its input is this e squared divided by 1 plus e squared the whole square times the incoming gradient. If there's a gradient of G with respect to itself, that's 1. Okay. Like for example, here in this multiplication node, what is this local gradient? Gradient of C, which is this intermediate edge with respect to A, is x, and gradient of C with respect to x is A. Okay, those are the local gradients. Those local gradients can be multiplied with whatever is being returned back. Okay, whatever is sent back on the edge C. Okay, so you start with the local gradient, you send it back, gradient of G with respect to Z. Now Z is an addition term, very similar to the previous example. So this local gradient again is sent back to both the edges C and D, and C and D are just multipliers. So for example, if we focus on the C side, so gradient of G with respect to C is whatever was the incoming gradient, times the local gradient here at Z. Let me go one step forward. So if you look at the final gradient of G with respect to Y, is a local gradient here times the local gradient here times the local gradient here times the incoming gradient. Okay, so it's just, so G with respect to Y is gradient of G with respect to D times gradient of D with respect to Y, and gradient of G with respect to D is again gradient of G with respect to Z times the gradient of Z with respect to D. Sorry, I'm just repeating the terms again and again. So, but chain rule is just this. Okay, gradient of G with respect to Y can be G with respect to Y is just the gradient with respect to Z, Z with respect to D, D with respect to Y. It's just a product of three things. That's chain. That's a chain of intermediate gradients that you're computing to intermediate partial derivatives you're computing to get the full partial derivative. Okay. So any questions? I know we are running out of time, but I wanted to at least discuss these two examples. So let's actually come back. So, okay, these are examples, have some details. So let's actually come back to what's going on. Backpropagation is the idea that if I want to compute the gradient of, let's say, some final quantity with respect to some inputs, okay, you just have to take the incoming gradient. Okay, where is the incoming gradient coming from? From some next computation node. Okay, they'll send back some gradient, take that gradient, multiply with the local gradient that you have. Local gradient is just what is the gradient of h with respect to A, what's the gradient of h with respect to B. If you have those two, take the incoming gradient, multiply it with the local gradient, and send it back to whoever is connected to you. Okay, so you just have to think in terms of myopically, hey, at each computation node, take some incoming gradient, multiply with the local gradients, send it back. Okay. As long as you can do that, then you can actually compute the gradient of whatever, like for example, loss with respect to parameters, no matter how complicated the computation graph is. Like it may have lots of nodes, connected to each other connected to each other in several ways, eventually leading to a loss value. So you can find the loss with respect to parameters by just passing back the gradients and multiplying locally, passing it back, multiplying it locally, passing it back, and that's just chain rule. Okay. So we'll pick this back up, briefly review it next class, and I'll also show why logistic regression fails for even 2D data, which will motivate us towards using non-linearity and introduce us to our first neural network models. First, I guess, non-trivial neural network models, which are just feed-forward neural network models. Okay, so that's we'll do next class. But in the meantime, if you have if you want to try out, get started on Python and so on, I would say clone this repository or download this, go to the examples, and try running this this linear classifier example. Okay, or you can look at the assignment. It will tell you what are the moving components here. Assignment 1, what are the moving components here. But you can try this this example, which exactly mirrors what we saw today. Hey, what is the data? What is the model? This is the optimization loop, and you can score. You can say what is the performance. Okay, it doesn't reuse any complicated packages, just NumPy and plotting, and so it'll give you a sense of like how does the training loop look like. And this is just implementing logistic regression. Okay, I think we went over a couple of minutes. So any questions, please stay back. I'll end the recording now, and you can ask questions, or you can also send me an email, or you can also ask it in the chat right now. So thank you.